Hi everyone, thanks for coming. We're very happy to have Arushi visiting from the University of Maryland, and she's going to tell us about stochastic gravitational wave and isotropies. Whenever you're ready.
Thank you, sir. Thank you so much for the invitation to talk here. I'm really excited to tell you about our recent work on stochastic gravitational wave anisotropies and how it can be used as a window into multi-field inflation. And this work has been done with my advisor, Raman Sundram at the University of Maryland. And please feel free to stop me and ask questions at any point.
So what makes you sure that the 2 in the second paper is not a 2, is not a 3?
I'm an optimist, and the fact that it's 90% written tells me.
Very good.
Well, we'll take a picture and hold you to it, okay?
Yes, sure.
It's very important.
Actually, good for me too. It gives me, puts a deadline on me. Okay, so.
That's why not. Why don't you just use your computer if you don't mind?
Yeah.
Yes.
Oh, I think it's because the recording.
Okay.
Oh, wait.
You might have to click.
Actually, this might work.
Okay.
Wonderful. Okay, so the rough outline of the talk is as follows. First, I want to give you some background and motivation for why we want to think about isocurvature gravitational wave backgrounds. And after that, we want to kind of ask questions about this general theme that what can we learn specifically about isocurvature gravitational wave background that we already haven't learned from the CMB, which is adiabatic perturbations. And on that theme, we want to ask 2 questions, like the size and shape of the anisotropy. So by size, I mean, what does the size or how large these anisotropies are, what does that tell us about the early universe fields? And we're going to give you the answer. We're going to learn about new light fields from the size. And then we also want to ask what are the detection prospects at upcoming gravitational wave experiments. And the second part of my talk, I want to focus on what is the shape of these anisotropies tell us. For example, we know that in CMB, there could be different new physics during inflation can introduce features like bumps, oscillations, non-Gaussianities. We haven't seen that in the CMB, but we want to ask, can such features appear in the isocurvature gravitational wave background? And what can they tell us? And again, the answer is we will hopefully learn about heavy fields during inflation from studying the shape of these anisotropies. And so this basically roughly distributed between 2 recent works. Yeah, so as a starting point, I think we all will agree that the cosmology has become important aspect of particle physics exploration, mostly because as the universe cooled down, like from the Big Bang cooled down, it went through a large range of energies. And so it kind of gives us access to new physics at very high energies. Now, experiments like CMB, large-scale structures, they tell us about particle physics at EV MEV range, but also in the super horizon, the causally disconnected patches and correlations across them at the time of CMB tell us about very, very high energies that could have existed during inflation. However, there is this kind of dark kind of age between MEV to inflation where we don't really have any observables from this era. And mostly because in this time, the standard model is highly interacting goo of things and nothing kind of escapes from it. So we don't really get any observables from this time. However, this is not true for gravitational waves, because if there's any source of gravitational waves at this time and releases gravitational waves, they will just free stream after that because they interact very weakly with everything else. And we can actually get an observable from this era, which is kind of the dark ages. So gravitational waves are interesting in that aspect. Now, cosmologically, there are various sources of gravitational waves that we can consider. For example, first order phase transition, cosmic strings, they can be produced through preheating, produced at second order in scalar perturbations. Today, I want to focus on first order phase transitions as the source of gravitational waves, mostly because strong first order phase transitions can give detectably large signals typically. So they're good sources of gravitational waves. Also, many BSM models have kind of predict phase transitions in a multi-TeV range, which nicely falls within the frequency range of many upcoming gravitational wave experiments. For example, here I'm showing a kind of sensitivity plot of Lisa as a function of frequency. The blue thing tells us the sensitivity of Lisa, and this black curve is the predicted gravitational wave signal if a phase transition is happening at around a TeV. And it just kind of nicely falls within the sensitivity region.
What takes this range 1 to 1,000 TeV from viewpoint of BSM models?
I guess if you think about like Suzy and it shows up around a few TeV, then that's mostly the reason.
We all know Susie shows up.
People have been saying that for 30 years.
Maybe 1,000 TeV, but yeah, I understand the argument.
No, I'm just.
How would that move with energy? So then
Yes, good. So if a phase transition happens at higher temperature, it moves towards the right, the spectrum.
you're right.
So why phase transitions give gravitational waves is phase transitions characterized by development of a true vacuum away from the false vacuum in which your system is. And when the system transitions from the false vacuum to the true vacuum, either through tunneling or thermal fluctuations, it forms kind of these nucleation sites of true vacuum, which kind of expand and form these bubbles of true vacuum. And when the bubbles collide, it has a time-dependent quadrupole moment, which gives off gravitational waves. And that's kind of the source of gravitational waves for us.
So in the, just curiosity, in the field you draw a line, what are the uncertainties on those lines? So because this is not a simple process, right? So
Yes.
it must depend a lot on the velocity of propagation. So
so the amplitude, so the general shape does have a little dependence on the microphysics, as I'll also say. This part, the low frequency part is pretty much common to all phase transitions because it's actually coming from kind of, these are super horizon modes at the time of phase transition. They don't get affected by causal physics. But yeah, the peak and the exact shape does change a little bit. And of course, the height changes based on like how strong your phase transition is. Yeah. But for us, because we're not, as I'll say, like we're not really interested in studying the shape, but like what more on the anisotropy part. So yeah.
thank you.
And you detect this thing because you detect some kind of bump as a function of frequency? Because otherwise it's just some diffuse stochastic.
Yes. So I think
how
to
do I
infer.
distinguish it from just some random noise in the detector?
Yeah, so I think if you want to pin it down to like the phase transitions as the source, then the frequency spectrum, you want to get this frequency spectrum, and different sources have different shape of the frequency spectrum. But yeah, I mean, it's going to be a stochastic background. So in your like strain as a function of time, it will just show up like this. So you have to like filter out and find out you have to filter it out from the noise and then plot its frequency spectrum, and then if you see the bump, then you know it's from a phase transition.
Is that something that's really hard to do? Because I mean, in the current detections, they rely heavily on the fact that there really is some, chirp.
Yes.
And for which they have templates.
Yeah. So I think yes, you're right.
You can dig things that are way below the noise floor. Because the signal has some.
It is very difficult, but apparently, I mean, there was a workshop dedicated to it a few weeks ago at KICP, and apparently people think they still have some handle because they have two detectors. There's still some time coincidence that you can correlate, and apparently people think that based on that you can do it. You can still do it. Okay, well, we'll have to see. You have to demonstrate they actually see the thing that they expect to be there, namely the unresolved merger. So these are stochastic. So once they see that, we have more confidence we can see something.
So the idea is that you have the same frequency spectrum appearing as noise in many detectors, and then when you cross-correlate the data between those two detectors, the noise pops up. So you have to assume a model for the spectrum. So say you assume f square or whatever, and then you search for that f square feature in the noise across detectors by cross-correlating.
Yeah, I think you need multiple. You have to cross-correlate between detectors to reduce because the noise will not be correlated, but the background would be. So you really need like this time delayed interferometry.
But they still have to
stochastic.
demonstrate that they can see
Yes.
this. Okay, I see.
Yeah, and I think a
share,
bigger problem is astrophysical stochastic foreground
yeah.
and removing that.
And with LIGO, we do have 2 detectors, but LISA is just 1 detector, right?
No,
But it's made up of, it's like a triangle. Made up of
Three.
3.
Oh, it's 3, okay.
Pathfinder is
Actually,
one. The going to be 3.
Already seeing those 3 detectors in space would be fantastic, right?
Yes, yes.
Even if they don't work.
Someone set a very high standard for that. Okay. But for the phase transition, what the regime I mean, which paper is this? They're thinking about
This is an old paper where people even propose that stochastic gravitational, like the gravitational wave background will
Yeah,
the
but
gravitational waves will be
the
released.
phase transition, the actual shape depends on whether the time scale of the phase transition.
Oh yes, so yeah, as I said, yeah, so this peak and the exact shape at the peak does depend on this beta parameter.
Yeah, they must be assuming something about beta.
I mean here I have assumed like so there's like this nice tool PT plot that the LISA where you can actually just give your parameters and get a frequency curve. So it's a beta of 10 here, 10 Hubbles at the time of phase transition.
That you should actually see some oscillation.
Oh yeah, if there's a phase transition during inflation.
Yeah.
So this phase transition is happening after inflation.
Oh, this is after inflation.
Yeah, it's happening in that
Yeah.
period. Yeah.
Okay.
Yeah. So we established that the gravitational waves are released from phase transitions, and when this phase transition happens, it's happening everywhere in space. So today we expect to get gravitational waves from all directions if the such phase transition happens. So you create a background of gravitational waves, just like the CMB. And I do want to caution that here I have kind of really zoomed into this picture of bubble collisions, because on the sky, in a very small patch of the sky today, there will be a ridiculously large number of bubble collisions actually happening. So what you're getting is like an incoherent superposition of gravitational waves from all these bubbles. So we are not actually resolving these bubbles. So the bubbles are not resolvable, but they just give you gravitational waves which will track large density fluctuations of the plasma as we'll see. Okay, so there are 2 aspects. If such gravitational wave background is detected, there are 2 aspects of it that we can study. The one that is typically focused on in the literature is the frequency spectrum, as I said, because it gives you information about the causal physics at the time of the phase transition, and we can refer to it as a sub-horizon physics. However, in this talk, we want to focus on the anisotropies, which tell you information about causally disconnected correlations across causally disconnected patches at the time of phase transition. So since the microphysics of the phase transition cannot affect super horizon fluctuations, they must be set in from the time of the inflation. So these super horizon correlations across causally disconnected patches actually tell us directly about the information that is coming from inflation. And these are completely complementary informations. One is sub-horizon, one is super horizon. So because we're interested in inflationary physics, we'll focus on the anisotropies of these gravitational wave backgrounds. And there's a kind of analogy with CMB that just across, if you point your detector in different directions in the sky, you will just see hot and cold spots, and you'll create like this map of fluctuations across the sky. However, there's one important difference between CMB and gravitational waves, that in theory, gravitational wave background would create a more pristine map of anisotropies. And the reason is simple. So in the CMB, here I'm showing like a 2-point correlations of temperature fluctuations across the sky in multipole space. And we all have seen this picture with like these bumps, and we know that these bumps actually come from acoustic oscillations, which are kind of a sub-horizon phenomena, like causal physics. And it starts at L of 30 because that's the horizon size, the angular size corresponding to the horizon size at the time of CMB. And before that, we see this flat spectrum, which we expect from the scale invariant spectrum that we expect from inflation. After that, you have kind of infection from causal physics in CMB. However, this dividing line between super horizon modes and sub-horizon modes in the gravitational wave would be all the way to like really high L's, because gravitational waves are produced earlier, so the Hubble horizon size at the phase transition is much smaller in the sky today, an angular size. So you get this large range of L modes where you have no infection from sub-horizon or causal physics, and your cosmic variance keeps decreasing. So you have like a large range of L's in principle, where you're directly seeing inflationary fluctuations. Now to see how these gravitational wave backgrounds are created, which will help us, let's do a recap of CMB and anisotropies. So in the CMB, here I'm in purple, I have surface of constant temperature at last scattering. If the universe was completely homogeneous, I would expect this to be a perfect sphere around us. But we know that there are small inhomogeneities. So the patches in the direction where the plasma is hotter, this constant temperature surface will be closer to us. And the photons coming from there will not be as redshifted. On the other hand, the patches which are colder will be further from us, and the photons will get more redshifted on the way to us. So it creates this cold and hot spots across the sky. And we know that it looks something like this today, but the temperature anisotropies are very small at the level of 10 to the power minus 5. Now we can apply the same logic for gravitational waves. And in pink, we can draw the surface of constant critical temperature, which is the temperature when the phase transition is happening. And similar to the CMB plasma, there will be some hot regions, some cold regions. So gravitational waves from hotter regions will not be as redshifted, while the gravitational waves from colder regions will be more redshifted, creating a similar hot, cold spot picture for the gravitational wave energy density as well. Now, if the plasma producing gravitational waves on CMB is the same, then we'll expect a perfectly correlated gravitational wave background anisotropies, or the adiabatic, that's what I call adiabatic gravitational waves at the level of 10 to the power minus 5. But this source doesn't have to be the same. If the gravitational waves are produced from a completely different sector or fluid, then the anisotropies of gravitational waves will not correlate with the standard with the CMB. And in that case, they will be isocurvature in nature. And in particular, they could be much larger than the anisotropies that we see in CMB. And they could contain all sorts of interesting features that the adiabatic perturbations do not contain. So these are the two aspects we want to explore. So we want to ask, like, what can this alternate source be? And one example could be an axion-like particle, which is a light field during inflation. And by light, I mean its mass is lighter than the inflationary Hubble scale. And we want it to actually have some energy density so that we can get gravitational waves from it. So we'll consider an initially misaligned alpha field. Let's call it chi from now on. And initially, this will be stuck here due to Hubble friction. And I want to say that this is kind of a spectator field. It's not driving inflation. The inflation is still driven by the inflaton field, which is phi. But it's some kind of field with subdominant energy density. And just like how inflaton gets quantum fluctuation, this alpha field during inflation will get quantum fluctuations and develop a nearly scale invariant spectrum of fluctuations. And across the spacetime, because it will have plus minus Hubble in field space, it will have its energy density will also fluctuate across space. And the level of anisotropy, which is delta chi, which is just a ratio of how much variation there is in potential energy over some average potential energy, it will be given by the inflationary Hubble scale over this initial misalignment chi naught. And as you can see, this is completely different from the fluctuations in the phi or the inflaton, which will give us CMB. And when we will take this in our model, we will say that when the Hubble, after inflation as the Hubble is dropping, when the Hubble reaches the mass of this chi field, it will start oscillating and it will reheat some radiation sector and transfer its anisotropy to that radiation sector. And then that sector will undergo a first order phase transition, transferring the anisotropy of chi to the gravitational waves, hence creating isocurvature gravitational waves.
Sorry, you're imagining this does not affect the CMB isocurvature bound?
Oh yes, so yeah, we will have to worry about all that. So we'll get constrained.
You did worry about that. Okay.
Yes, we will worry about that.
We will later on in the talk.
Yes.
Okay.
Yeah, yes, we will worry about that.
No, because you can also assume this somehow there's some slightly more complicated model. This only fluctuates at the shorter scales, smaller scales. So then it doesn't have to affect the CMB scale. But
Yeah, one could consider a blue tilted spectrum,
Yeah,
like you're saying,
blue
that only
tilted, yeah.
has large perturbation on
Yeah.
small scales. However, like if you look at from the detection perspective, initially you will only have, it's easier to detect large L or like small L perturbations or large scale anisotropies because you need more and more resolution to go to larger L. So if you have a blue tilted spectrum, it becomes harder experimentally to like even detect any anisotropy. So we
okay, but then you have to worry about CMB.
yeah, and I will. So yeah, so for that reason, I'm going to consider a nearly scale invariant spectrum, and then I'll have to worry about isocurvature and everything. Oh yeah, so with this we can kind of we can construct a simple model which gives us our isocurvature gravitational wave background. And in this picture, it's easier to think about these scenarios in terms of this energy density versus time
Right,
kind of
just
diagrams.
another question. This spectator does not dominate later on, right? It just decays as part of.
I'll come to that.
Okay.
Yeah, so in this sector it doesn't. In the simple scenario it doesn't actually dominate. So
Otherwise, it's not isocurvature. Otherwise, it's curvature. Otherwise, if it is not dominating, then
yes, exactly. Yeah, so if this chi actually dominated the energy density at some point and just
then it becomes curvature.
then it becomes curvature scenario. But we don't want we
don't
want an
curvature, You
isocurvature.
want isocurvature, so
Yeah.
it cannot dominate.
Exactly. Or okay.
Alright.
I got
Alright.
that. There is, yes, but you're right. So it's easier to think about this scenario in terms of these kind of diagrams where on x-axis I have time, basically on the y-axis I have energy density, and in this way if a radiation will just dilute like a to the -4, so it's like a straight line, it just keeps decreasing. And so we can see that, let's see what everything is doing. So our app field or chi is constant till its mass becomes comparable to Hubble, and then it will quickly decay and transfer its energy into a sector, we'll call it the phase transitioning sector or PT sector. And we'll take it to be some extension of the standard model that can give us phase transition in the multi-TeV range for the detection, from the detection point of view. So it decays into this phase transitioning sector. It will undergo a phase transition in the multi-TeV range, gives us gravitational waves, and keeps diluting like radiation. Now inflaton, which is the dominant energy source during inflation, driving inflation, will actually at the end of it will reheat into some non-PT sector or some hidden sector that does not participate in the phase transition and is very weakly interacting with this extension of standard model. And hence, because it's weakly interacting, it will be stable for a long time, and only at some point when its decay lifetime is comparable to the age of the universe, it will decay into standard model at some later time. But it will decay at a temperature lower than the phase transition temperature. So this sector never participates in the phase transition. Okay? And at the end, whatever is a standard model plasma is a combination of whatever is coming from the alp and whatever is coming from the phi, but dominantly things coming from the phi. So we see that the CMB is going to get dominantly perturbations from the inflaton, and the gravitational waves are going to get perturbations from chi, creating an isocurvature gravitational wave. And this scenario, I must say, was actually discussed in this paper by the authors at Maryland. Just to be precise, let's see what are the perturbations in the CMB and gravitational wave. As expected, perturbations in the CMB are dominantly coming from the perturbations of inflaton, and for the gravitational wave, dominantly perturbations of chi. But because you're talking about two fluids on the cosmic timescale, there are infections from the sectors into each other's anisotropies. So for example, at the end, the standard model is composed of decay products of both inflaton and chi. So there is some infection from the chi sector into the anisotropy of CMB, but it's always weighted by the smaller fraction FPT because this sector, phase transitioning sector, is subdominant to the non-PT sector. So that ratio is the weight factor of its contribution in the CMB. And similarly, the gravitational waves have this infection from the fluctuations of this non-PT sector or delta phi, and that's just the Sachs-Wolf kind of contribution at the level of 10 to the power minus 5. And we'll see that these infections actually give us constraints and will be important when we analyze the scenario. For example, let's focus on this to figure out what is the interesting range of delta gravitational waves that tells us anything about our chi field. And clearly, if the delta chi, which is the anisotropy in the alp sector, is much smaller than 10 to the power minus 5, it will be completely hidden under the Sachs-Wolf contribution and its cosmic variance. So you will not actually be able to say anything about the light field. However, if the delta chi is bigger than 10 to the power minus 5, it will imply that there has to be, it's isocurvature and has to come from some other light field. So a gravitational wave and hence delta chi of greater than 10 to the power minus 5 directly implies existence of another light degree of freedom, another light field or quantum field during inflation. Yeah. Not only that, the exact the amount, like the amplitude of this delta chi will also tell us about some fundamental parameter of this chi field. For example, if I measure delta gravitational wave bigger than 10 to the power minus 5, I know it must be coming from some relation like this. And if I know h of the inflation from measurement of tensor to scalar ratio or some other method, then I can directly infer what is the initial misalignment of this field. And lastly, another motivation for considering large delta chi is like if you have high scale inflation where you're saturating the H inflation to maximum it can be from today's constraints, then all you need is a sub-Planckian chi naught to get delta chi bigger than 10 to the power minus 5, which makes it more likely. So coming back to our contents, we did address what is the interesting size of gravitational wave background, and we know that will tell us about light fields. But then we also have to consider what are the constraints on it from the isocurvature, etc., and what are the detection prospects in the upcoming gravitational wave experiments. And as was correctly pointed out, if I have isocurvature, especially large isocurvature, I need to make sure that it doesn't show up in the CMB. So what that means is if my delta chi is large, which is observationally more interesting, I have to reduce the fraction of energy density in chi compared to the energy density coming from phi. So this fraction FPT has to decrease if I increase delta chi. And we'll see that this actually hurts us because if I consider radiation domination throughout, this means that the phase transitioning sector is also subdominant at the time of phase transition. And it means that it will actually it will hurt us by reducing the strength of the gravitational wave that we get. And to see what is the price of having this small fraction, let us look at how what is the energy density of gravitational waves coming from phase transition. So here I have omega gravitational wave, which is typically how gravitational wave strength is measured, which is just the ratio of energy density in gravitational waves to total energy density in the universe. And it depends on some microphysical parameters of the phase transition, but what I want you to focus on is this factor, which is the ratio of the phase energy density in a PT sector to the total energy density. And why we expect this to go as a square of rho PT is simply if you write down Einstein's equations, you'll see that the strain of your gravitational wave is sourced by this rho pt, so it should be proportional to rho pt. But the gravitational wave energy density itself goes as the square of the strain. So you expect a square of energy density in the phase function sector. And if you remember, this is the exact factor of FPT that is helping us evade CMB constraints, but now it's hurting us by suppressing gravitational wave signal quadratically. And if I consider anisotropies, which is what I'm interested in, and I take the isotropic gravitational wave signal, multiply by delta chi, and even if I put like the best case scenario where this FPT delta chi can be at most 10 to the power minus 5, I still have 1 power of suppression in the anisotropies with this factor FPTs. And to see from the experimental perspective how bad is the situation, I want to compare it to the sensitivity of various gravitational wave detectors to anisotropies. So here on the right, I'm showing sensitivity curves for various gravitational wave experiments and in the multipole space. So this tells me that this is kind of the fake anisotropy every detector will have, or the noise power spectrum of the detector. It was actually studied in these papers. And as you see that the sensitivity actually drops at higher L with most of the gravitational wave detectors, so it's already harder to see anisotropies at large L. But let's see with our extra suppression, we'll see that this makes it even worse. So if I now consider various benchmark points where I have different values of delta chi, increasing values of delta chi, what I'll do is I'll take the best case scenario where this FPT delta chi is maximum, which is at 10 to the power minus 5. I'll consider some beta of 10, reasonable beta. And I'll see that with these numbers, I can evaluate what is the anisotropy power spectrum of my gravitational waves. Because it's scale invariant, it will be just flat, and I can lay it on top of these sensitivity curves. I see that if I increase my delta chi, the signal itself, that measurable signal, just drops very, very fast. It becomes really hard to see large deltas because of this FPT suppression.
Excuse me. So for given phase transition model, when the FPT gets smaller, how does beta over H changes?
It doesn't. Beta over H is just a property of the phase transition. It doesn't really.
So there usually let's see. Also the hyper expansion rate is important. I mean when some path is a subdominant component of the universe, for given temperature, expansion rate of the universe gets larger. So that typically delay the phase transition or lower the nucleation temperature. So my question is how does that change the typical beta over H?
Oh yeah, so
can't achievable even for conformal model.
Yeah, so we checked that you're right, that if I change H, which depends on the total energy density, it actually also changes beta, such that the beta over H combination remains the same, and it's just completely determined by the bounce action of the phase transitioning sector, etc. So it doesn't. You can just independently select the ratio itself.
Okay.
What is the time scale for all these gravitational wave experiments? BBO and ultimate the SIGO?
So LISA is already
That
approved.
I know, yeah.
So yeah, so my aim is to bring these in the LISA detectivity.
I see. Very good.
Because LISA is the most promising. It's planned and it's getting made. The others are kind of based on LISA design, but bigger and more ambitious. So they're harder, and I don't even know the timeline, to be honest.
Are you sure we don't do better by going to smaller scales?
I mean, by going to smaller scales, it's just going to get harder.
But you are not subject to isocurvature bound anymore. You're not subject to CMB isocurvature bound anymore.
I see what you're saying. So
yeah, so you can
but
relax
I mean this L is still within. So if I want to escape the isocurvature bound, then I have to go to L of more than 1,000 when you have cell damping and whatnot.
Yeah, but
I mean, this is at 30 and it's already it gets harder for these experiments to go to larger L or smaller angular scales.
So
I mean,
think
if
because
there-
your problem is really you need to see anisotropy.
I mean, yeah, if I didn't like demand that I want to see it at LISA or something, then I can say, okay, I'm pretty sure if you detect such a background, the next step is people will think about anisotropies and they'll build detectors which are specialized for that. And then you'll have better sensitivity than whatever is projected here.
Right.
And that case, it would, then the blue
You just
tinted
somehow
spectrum, etc.,
learn
would be
how
more
to
interesting.
aim. Somehow learn how to aim.
Yeah, so here I wanted to go with kind of theoretically interesting, and also I can say something about experimental things.
Okay.
Yeah, so our aim would be to like see if I can target like these large anisotropies at LISA. At least a few multiples here, like this one is. Okay, so that's our aim. Can we do better? Is this inevitable, or can we get rid of this FPT suppression? And the simple point is that to notice that whatever helps us evade CMB constraints is also hurting us because there is radiation domination throughout. So what we want is we want this FPT to be 1 at phase transition, but we want it to become smaller later by the time of CMB. And a simple way to do that would be to notice that different fluids dilute differently. Like radiation dilutes the fastest, while matter, if you have anything behaving like matter, dilutes slower than radiation. So what we are going to do is we are going to start with a curvaton-like scenario where chi actually becomes dominant before decaying. So when the chi decays, it's actually dominating the energy density over phi. And then, so when the phase transition happens, the PT sector is dominant. However, at some later time, some particle in this hidden sector that is reheated by phi will become non-relativistic, dilute like matter. So it will be able to gain over the faster dilution in the radiation.
Later, at some point later, a reheaton dominates.
Yes, exactly. Yeah. Exactly. So you have initially you think about like you go into a curvaton-like scenario, but as you said, you want an isocurvature gravitational wave background. So you have to somehow make the phi sector dominate later, so you can do a reheaton-like story.
But that reheaton is generated from the inflaton.
Yes. Yeah.
Because you want to inherit the inflatons.
Yes, exactly. Yeah. And so in this time, you don't want any thermalization happening between the two sectors. So they have to be kept separate so that the sector doesn't affect gravitational waves and just only
So
contributes to
when
CMB.
inflaton decays, it goes to reheaton or what? Goes to
Yeah, it can go to reheaton. It can go to some something that has a particle that can become non-relativistic, basically, without like.
I mean, I imagine you have a specific model, or you just.
I mean,
talking about this scenario that.
I know in literature that people have talked about this kind of scenario where there's a reheaton and with a reasonable mass with reasonable coupling, and it can. Okay, so just to finish the story, afterwards we want it to decay into standard model because that's what we see. So it will decay later, and I mean, if you have like this particle with like mass of, I think I calculated it, it's like 10 to the power 7 TeV, and if it's just, even if it's just coupled like M Planck suppressed coupling to the standard model will give you correct decay and the correct amount of matter domination, etc. So you can build a model where
it doesn't reheat it to the right temperature.
Yeah, it reheats at the right temperature. It gives you correct period, and that's just like even kind of M Planck suppressed coupling. You can of course have some small couplings which are bigger than that and can change the amount of matter domination you get or when you reheat, etc. But I'm saying that you can build a model.
It changes a bit of how the gravitational wave is redshifted as well, because you have this matter domination.
Yes, yes. So of course, yes. So as you see that here, what we're using to dilute this PT sector will also dilute gravitational waves. You're correct, but it doesn't do it. It doesn't give as much. It's not that bad.
It's not as bad.
Yeah, exactly. So just to go through it. So at least at the production, we don't expect any suppression because the phase transition is just a dominant sector.
See, here is the fluctuation of this matter is correlated with that of inflaton, not with this ARC product.
I guess it's part of
Say that
it.
again?
So the fluctuation of this matter is correlated only with inflation, and it's not correlated with this half decay product.
Yes, yes. So
Okay.
at least, so for large scales, which are what are relevant for CMB, the fluctuations of this matter or this entire sector will be completely inherited from phi. On small scales, however, which are entering the horizon, when this is happening, there is gravitational inflection, so you have to worry about that. But at least for CMB, it's going to
Okay.
not cause any problem. But yeah, as was correctly pointed out, you don't have any suppression of the production, but you have this like entropy injection because of this matter. So you do have some dilution of the gravitational waves. However, if you calculate correctly, this early matter domination period is exactly related to the fraction FPT that you want at the end.
Yeah.
And you get exactly one factor of suppression in your
Okay, so
gravitational instead
it's
of
a little
431.
better, I think.
Yeah.
Okay.
And then if I just find out in anisotropy, there is no extra suppression of FPT if I just put this to maximum value of 10 to the power minus 5. And how good the things become is I'm basically if I take the same benchmark points and now the same best case scenario that I was considering previously, I have no extra suppression of FPT. So all these benchmark points just collapse into this one line instead of like getting suppressed. So basically, if I'm lucky to some extent, I can have a large anisotropy detected at LISA, at least to first few multiples here.
It's literally like the east different from west. Just divide the sky into two pieces. This part
Yeah,
is
and the 4 is slightly better.
Okay.
Not just north. But yeah, and of course here I think there's the LISA is run like they take 4 years to do the sensitivity because they have 4 years.
This is still weak scale phase transition, right? You're still assuming
TV scale.
TV
scale. Yeah, TV
What
scale.
happened? You changed the scale.
Yeah, so if you change the scale, the whole spectrum moves,
Yeah.
and if you have
But the amplitude can also be. Oh, I guess.
actually amplitude
Yeah, it's probably
does
the
not really
same.
depend on the temperature, but more on these beta parameters and like how much
Right.
different other parameters, but not specifically on the temperature. Temperature mostly just tells you
Right,
where
right.
you expect the spectrum to be.
So in typical part of the model, beta is say 100 to 1,000 times h. What happened in that case? Can we still detect this anisotropy?
Yeah, so actually if beta is larger, that means your phase function is smaller, so you actually generally get lower gravitational wave signal. So it will be probably harder to do it at LISA. You'll have to go to better sensitivity instruments. But that's just true even to do isotropic signal. High betas are generally harder with LISA. You have to go to BBO or DCycle.
Yeah. It's at least 1/beta squared.
I know that. Okay, one thing that saves you sort of is if you have higher beta, the bubble collision the bubble wall contribution goes down, but the sound wave and turbulence contributions actually not is one less power of beta suppression. So
Okay.
that's slightly better. But generally larger betas are harder to see. But considering still we see something, I think one can be optimistic. Or till we don't see anything, we can be optimistic, I guess.
What about second order phase? Sorry, what about second order phase transitions?
I think they don't really, because you really need those anisotropic bubble collisions which give you order 1 anisotropy in space time. So the second order phase transition doesn't.
Transition also, you sort of
defects.
Hubble,
right.
Hubble and Hubble wise is different, right? So you still have in this Hubble patch that happens earlier, that Hubble patch happens later, and so because it correlated with temperature.
Yes.
Right? So there's still something, I think it's just the question of whether.
Yeah, you're right. So it can have that, but then you need some messenger in some sense to detect that
Well, I thought you were just going to see the gravitational wave.
But the second order doesn't produce gravitational waves.
It does, but it's just not as big. I think it's not as.
What is the source of the gravitational waves in that?
Like this, it generates gravitational.
Oh, I see,
I see.
like preheating kind of thing.
Any amount of ion,
Yeah.
non-evenness in the space.
I see,
As long as you have some quadrupole, you.
But it's not a violent effect like here, so
It's probably not
the
as
amplitude
violent,
will be
yeah.
very small.
Yeah, you're right. I know that in this like the preheating source that I talked about, if you have
Yeah.
like
If you have
fast
preheating, it
enough,
will be better.
then you can, and if you can like kind of tune when it starts by some other field, like modulate this, then
if you do that.
actually that can be another way to do this. True.
I'm sorry that I bug you again with this, but
Yeah.
it's simple ignorance. I don't know those curves that you draw like straight lines. There must be a large uncertainty in all these things, right?
Oh yeah, so here
So-
I can draw relatively straight lines is because it's a light field during inflation. So I know
No,
it will have,
the detector part,
No, you
Sorry, but
mean
just
the
the
prediction
total-
from first order physics?
the noise.
Oh, the noise, yeah.
Yeah.
So this is the kind of, even if there is no background, this is the sensitivity of this, the fake noise that the instrument is creating, these colored
These
lines.
are their study, right?
They are where does those lines, where do
Yeah, so basically these lines tell me that if I look at anisotropy of gravitational background at the certain L, this is the sensitivity of so this is the sensitivity of
Okay, well,
LISA, let's say, BBO.
but this is
or
computed
SIO.
by Lisa or computed?
So this was computed by these folks. I had it in the previous slide. So it's there
Who are the
was this
folks?
program.
Theory.
Theory folks.
Yeah, or like people
I
are
see.
working on actually.
Well, these are folks are not too different from theory folks these days. I don't think you have very
So-
good.
Where I took it from is there's a paper which did it for ground-based detectors as well as LISA, and they have this nice program called Schnell, which computes the noise spectrum.
Fast, I say.
Yeah, and it also has NL, which is the NL, the noise.
Yes.
Nice.
Press the wrong button. Yeah, so so NL, so Snell.
Very good, very good. Okay.
And then
Okay.
there was one more work which extended it to like include BBO and Disciple, because I think to get these curves, you really need to model how these detectors are going around, what is the trajectory as they go around the sun, basically.
Very good. Thank you.
Okay, so that's great. So this model actually gives us a lot of improvement by taking away a lot of this cost of having a small PT, FPT for large delta chi. But if you have worked on like early matter domination period, you know that there are constraints from like small scale fluctuations because they can have other consequences. Especially now in this model, we have a period where the fluctuations are large, the delta chi is large, and we have early matter domination in which the matter perturbations grow linearly. So one can wonder like what are the consequences, what are the constraints on this kind of model, and one has to kind of do a proper analysis what is happening to the subhorizon fluctuations, etc. But there are two important considerations that give us constraint. One is the enhanced production of primordial black holes, especially because primordial black holes generally feed off the tail of the distribution. But if you have early matter domination where they can grow, the production of primordial black holes is generally enhanced. So to make sure that you are not overproducing primordial black holes in this scenario, it actually constrains our delta chi to be smaller than this value of 0.03. So if you have anything bigger, you produce.
These are very small scales, right? These are very small scales.
Yeah, but the thing is, when primordial black holes form, they just act like matter throughout. So they actually can completely take over the other radiation that you have and overclose the universe. So these will be small and like, yeah. Are you saying that these are, if
No.
they're small, they'll just evaporate?
I'm just, again, I'm trying to imagine maybe the the model that responsible for generating the perturbations
Mhm.
that you care is are the perturbation you care are on large scales.
Yeah, so
Right?
the
So I think maybe the at small scales it's some different model that then you don't have to worry about this that much.
yes. Oh, I see. So you're saying if I have like if I consider some specific model where
Yeah, just you know.
yeah, I could get
I mean,
away.
okay. I mean, I'm just saying this is indirect, right?
Yeah,
This limit is indirect.
Yeah, because you're right. So the modes which are re-entering are very, very high as compared to the modes
Right,
which are
so this
observationally
one that you're
relevant.
not going to see otherwise.
Yeah, so this constraint, you're right, is for if you have scale, if you just want scale invariant spectrum, or even if it's slightly polluted, that's not going to help. You really need a spectrum that kind of is flat but then really drops at high K.
But model can change.
Yeah. I mean, yes, but like if I make it too contrived, then people will also have problems. So
Okay.
so because I kind of started with scale invariant spectrum, I would I give constraints on the scale. But you're right, like if I could think, if I could make a nice model where it just drops at large K, then I don't have to worry about all this. Yeah.
I'm confused. This chi behave as basically a radiation, and the decay product of chi is basically a radiation. Let's see. So what form this PPH? Which perturbation began PPH in this?
Yes. So right. So good. So generally, the subhorizon modes. So you're right. The perturbations are large in the PT sector, but that's acting like radiation. But what happens is when things become subhorizon, the perturbations from the chi sector transfer to the perturbations in this matter sector.
Okay.
Just because of gravity, which doesn't happen for super horizon modes, for subhorizon modes. And so you start with large fluctuations and they also grow. And so kind of see it's so to see like it really depends, the primordial black hole, the mass that they produce kind of depends on where this early matter domination is ending, etc. So what we did is we took this early matter domination to end at around 100 GeV because we wanted it to decay to standard model before dark matter decoupling in a WIMP-like scenario, if you have that scenario for dark matter, so that you don't form any other structures, which is on the constraint. So if I take that to be this, if I fix this point to around 100 GeV, then I interestingly get primordial black holes form in this like nice window. So in this plot, we have mass of the primordial black holes on the x-axis and the fraction of dark matter that they will form. And with this one kind of fixing that end of early matter domination, you get primordial black holes forming in this nice gap in the experiment. So you can actually have a significant amount of dark matter in this scenario coming from just primordial black holes. And also it has an interesting peak-like structure, and it's simply just this dynamics of these two sectors in the early universe, and which gives you kind of almost a monochromatic primordial black hole formation. And this mode is basically the mode that is re-entering right at the beginning of early matter domination. That's the mode that's giving largest energy density in primordial black holes. So this is, I've just considered the largest amount of primordial black holes that you can get without overproducing them. And so second important consideration is secondary gravitational waves, which are basically gravitational waves which are sourced by scalar perturbation but at second order. So this is another source of gravitational wave backgrounds. These are not coming from phase transition, but they're typically they're very small. If you just have inflationary perturbations, adiabatic ones, this contribution is ridiculously small. But now we have a period where the PT sector is dominating, which has larger perturbation. So they can produce larger amount of secondary gravitational waves. And they also have some interesting kind of features because of this interplay of two sectors. So let me just kind of show you one benchmark point to see how they look like. So in this plot, I have frequency on the x-axis and just the gravitational wave energy density today on the y-axis. And we saw that the phase transitions have this kind of peak kind of structure. So the black curves show phase transition. The yellow line is this contribution from secondary gravitational waves. And here the sensitivity of various future gravitational wave experiments. And I've done it for 2 benchmark points, the largest delta chi of 10 to the power minus 2, and then the delta chi of 10 to the power minus 3. So these secondary gravitational waves are highly sensitive to the level of anisotropy you have. So at the largest amount of anisotropy gives this curve, and if I reduce it by an order of magnitude, it's too small. It's not it cannot be seen on this plot.
Excuse me. I have a question.
Yeah.
So secondary gravitational wave depends on how RE matter dominated the ends.
Sorry, say
Yeah.
that again?
Yeah, so secondary gravitational waves depends on how RE matter dominated the ends.
How early?
Yeah.
But yeah.
It depends on how RE.
Yeah, so where this peak occurs will definitely depend on where the early matter domination ends, like what period in temperature this occupied. But because afterwards they just redshift like radiation till like radiation matter. So
yeah,
they're not going to relatively.
it sensitively depends on how the emitter ends. Yeah, actually, I've written a paper about that.
Okay. Yeah, I agree that.
Yeah, maybe that. Yeah, could you go back to that paper? Go back to the slide.
Go back.
Yeah, go back. Yeah, that paper is a bit old paper.
This one.
Yeah, that one.
Mm-hmm.
Yeah, so they don't.
Oh, do you mean? Oh, yes, I agree. So I think you're saying that the exact amount of secondary gravitational wave depends on how the early matter domination.
Heating occurs.
Oh, yes.
Yeah,
So
yeah.
I agree. So there are like 2 papers that talk about so this early matter domination, how violent it is actually can change the amount, like what the peak is. If it's a slow decay, then it's actually suppressed.
I've written that paper.
Yeah, and if it's fast, but the thing, so here I have actually just referred to the early matter domination without actually considering these effects. But because my guess is this is an overestimation, because to get any enhancement, you need a really quick decay.
Yeah, exactly.
Which generally is like if primordial black holes are evaporating, if the matter domination is coming from primordial black holes, so they evaporate generally very quickly, giving you an enhancement. But for us, it's like a reheat on that's like kind of perturbatively decaying into standard model. So
if we consider usual gradual reheating, like
then it's actually going to be smaller than this. Yeah.
That's what.
So this is like a conservative.
Conservative.
So I'm being safe here basically.
Okay.
It's actually I expect it to be actually smaller than
Arushi, we're at about an hour.
Interesting.
And people have been asking tons of questions. Are you somewhat close to a conclusion?
No. But okay, what I can do is I'll just advertise the second part, and if people are interested, they can talk to me, because I'll be around tomorrow as well.
That sounds perfect. Yes.
Okay. So secondary gravitational waves are there, and they can be interesting if you have like some, if in future you have other experiments probing this and you get this multi-peak distribution, and like you can infer early matter domination from this, because typically the secondary gravitational waves are just flat, but the early matter domination introduces this interesting kink. So if you can detect it, you can probably infer something about early matter domination as well. But however, you really need to get lucky, because they're very sensitive to whatever delta chi you have and quickly get suppressed. Okay, so that that was the first part where we thought about what is the interesting size of these anisotropies and what are the detection prospects. It looks like my judgment is really bad, but I have done this talk.
No, it's definitely our fault.
Okay, so the second part where I was going to talk about is because I promised you that we can probe multiple fields during inflation, I was going to tell you how different signatures in the power spectrum of gravitational waves can tell us about heavy fields, the cosmological collider type of things. So if people are interested, they can just talk to me.
If you want to show a couple plots here.
You have a plot, exactly, a plot that summarizes some, or that is too complicated.
Wait, let me think. No, actually, I don't have like one thought that could flash.
It's okay, I can ask you tomorrow, but.
Okay. Yeah. So I think like that kind of completes the story that like there are two different aspects of these anisotropies that tell us about two different
Very good.
things.
Okay. Thanks very much, Arushi. Any on-topic burning questions? Since we're we're a bit over time.
How long until tomorrow or a year?
I'll be around the whole day after this week.
So again, I should know this, but Lisa is going to be launched 2030, something like that?
Yeah, I think like 2030 or something, but it might.
Faster than FCC.
Much faster, that's for sure.
Yeah, that's
And
true.
at least it will be launched, yeah, contrary to FCC.
Yeah, I think the good news is that they have gotten money, so they're building things. Not in the proposal phase.
Lisa is on shop.
Great, now let's thank Arushi again. And indeed, Arushi will be around tomorrow, so
Sorry about making you go very long.
Yeah, I was.
This audience is much more ignorant than they